All right, so today we want to try to wind up our discussion of thermodynamics of small molecule absorption in polymers. And I want to just go back for a moment to the Sanchez-Lacombe model. We went through in a fair amount of detail the derivation of the Flory-Huggins equation to describe, for example, the thermodynamic activity of a small molecule in a rubbery polymer. And we mentioned that there were extensions to this. The Flory-Rayner model extends it to cross-link systems. The Pepys-Merrill model extends these thermodynamic concepts to cross-link networks where the system is, the cross-links are put in place in the presence of a solvent. And all of those models are lattice-based models, and they treat the polymer and the penetrant that are in it as if they're incompressible. And as a result of this, these models cannot predict any, say, temperature-driven expansion or contraction of polymers. They cannot be used to model things like pressure-driven compression of polymers. And Isaac Sanchez fixed that. And he fixed it by extending the Flory-Huggins model to include vacancies in the lattice that's used to model the thermodynamics of such systems. And having the vacancies there introduced the possibility that those vacancies could be removed with temperature or with pressure, and the material could be compressible. And it resulted in an equation of state that's shown here. We've gone over this previously. I won't belabor it, and gave essentially for the first time a fundamental model to predict, for example, density versus temperature for a wide variety of polymers and as a function of pressure. Now, this model has been used to describe small molecule absorption in rubbery polymers. And if one has the characteristic parameters for the polymer and also for the penetrant that's undergoing absorption, these predictions of solubility are without any adjustable parameters, and there are no other models that can do this among the ones we've talked about. Now, a lot of the polymers that are used in applications like gas separations, water purification, and controlled drug delivery are not equilibrium rubbery polymers. And all of the theories that we have talked about so far for solubility, with the exception of the empirical dual mode sorption model, they only apply to equilibrium materials, that is to rubbery polymers. And since a lot of the polymers that are used in applications are not rubbery, there is a real need to extend these thermodynamic models to glassy polymer systems or to non-equilibrium polymer systems. And Ferruccio Doglieri and Giulio Sarti at the University of Bologna did that, and they extended the Sanchez-Lacombe model to non-equilibrium or glassy materials. Now, we're not going to go through the derivation of that, but I'll show you some of the key features and how it's used in practice. And so the issue is that rigid, highly aromatic polymers like the one that's shown here, this is Ultem polyimide that's been used for gas separation applications, are glassy materials. That is, they have a glass transition temperature that's well above room temperature. This one's probably in excess of 300 degrees C. And what that means is that unless you heat this material above its glass transition temperature, it will behave as a rigid solid. It's amorphous, it's not crystalline, And if you heat it above its glass transition temperature, it will gradually start to flow like a viscous liquid. There are all kinds of glassy materials around you. The glass that's in the windows is a glassy material, and over periods of decades or hundreds of years, that glass can actually flow. Because it's not a rigid solid, it's a supercooled liquid with extremely high viscosity. It looks like a solid. And if you go to some of the very old churches, for example, in Europe, you'll find the stained glass windows are wider at the bottom than they are at the top. And this reflects, over periods of hundreds of years, slight flow of the glass due to gravity. Now, just looking at it for a few minutes during a visit, looks like a solid. But if you look at it over very long time scales, these materials are out of equilibrium and they can flow. Polymers have similar characteristics when, for example, at ambient temperature, they're well below their glass transition temperature. So for one characteristic of that we've seen before is a plot like this of specific volume, which is 1 over density, versus temperature. Okay, and so here you can see the TG of Ultem, it's around 200 C. If you start with this material at very high temperature, it would flow like a very viscous liquid. And as you cool it down, its specific volume goes down, that is, its density goes up, it shrinks, okay? And it does so by having molecular motions of the polymer chain segments reorient the material to a lower specific volume or a higher density that is consistent with being in equilibrium. Eventually, though, the rates of molecular motion get to be so low that as you cool the material, even at low rates, it can't keep up. The molecular motions can't reorganize the material so that it actually occupies the volume that it would want to occupy could it be in equilibrium. And depending upon how rapidly you cool it, you come out on a curve like this, or perhaps a bit higher or a bit lower depending on the cooling rate. And the material in this state now is not an equilibrium material, so it will not be described by thermodynamic theories that presuppose that the material is at equilibrium. Now, the issue and what Sardi and Dorgieri recognized is that these non-equilibrium states can be long-lived. They can be much longer lived than the time scale for an experiment, for example, to measure solubility of a penetrant in a polymer or transport of a penetrant through a polymer. And so Sardi and Dorgieri recognized that while the polymer might always be out of equilibrium, if you contacted it with a liquid or with a gaseous penetrant, that penetrant could be perfectly in thermodynamic equilibrium. And depending on how thin the sample is of this material, that equilibrium might only take seconds or fractions of a second to reach. And so what I mean by that is that the chemical potential of the penetrant inside the polymer can be exactly equal to the chemical potential of the penetrant outside the polymer if you have the polymer sitting in a bath of the penetrant. And at the same time, the material itself can be out of equilibrium. And so that's what's basically being said up here at the top. And so at these glassy conditions, the penetrants can sorb into the polymer and be in equilibrium themselves despite the fact that the polymer exists in an out of equilibrium state. Many or maybe even most of the polymers that are used in a lot of separations applications and a lot of applications where small molecule transport is important are out of equilibrium materials. And in all of those cases, you can have thermodynamic equilibrium of the penetrant inside and outside the polymer, even though the polymer itself is not at thermodynamic equilibrium. And so what Doguieri and Sarti did is they went back into the machinery of the Sanchez-Lacombe model and made a modification to it to reflect the fact that the material could be out of equilibrium. And I'm not going to go through this in great detail. This is the original expression for the Gibbs free energy of a low molecular weight fluid. That's component 1 and a polymer component 2. Rho tilde is the dimensionless density, T tilde is dimensionless temperature, R1 and R2 are parameters in the model, and Phi1 would be the volume fraction of the penetrant in the polymer. So this is directly from the Sanchez-Lacombe model expression of the Gibbs free energy of a polymer penetrant mixture. Then normally what you would do in the next step is you would take the derivative of the Gibbs free energy with respect to density, constant temperature, pressure, and set it equal to 0. And this would provide the criteria for thermodynamic equilibrium in the system. And it would then go on to give you expressions for chemical potential of both the polymer and the penetrant. And so what Sarti and Doguieri did was they relaxed this assumption. And what it means is that traditionally at equilibrium, the Gibbs free energy is at a minimum for a single component material is at a minimum for a given pressure and temperature. In an out of equilibrium material, the Gibbs free energy will not be at the minimum value it could be at that pressure and temperature, and so this derivative will not be equal to 0. And that's the change that Sarti and Doguieri made. And if you think about this in terms of concepts that you may have learned a long time ago, like the Gibbs phase rule, you can see how non-equilibrium materials work. And so essentially, if you have a polymer with no penetrant, no additive in it at all, and you apply the Gibbs phase rule, you would get that you have one component, that's the polymer. If it's in a single phase, like an amorphous material, that would be 1. And so the number of degrees of freedom would be 2. And that means that once you fix the temperature and pressure of that material, its density is fixed, right? This is how an ideal gas works, right? P times V hat equals RT. You can change any 2 of the independent variables, molar volume, pressure, and temperature, and the third one is automatically fixed. That is a direct consequence of the Gibbs phase rule and a consequence of the material being at equilibrium. However, a glassy polymer doesn't behave this way. At a given pressure and temperature, a glassy polymer, a non-equilibrium material, can have different values of density depending on how it got to that glassy state, whether you solvent cast it versus melt extruded it, how rapidly you evaporated solvent, how rapidly you cooled it if it was melt processed. And so at a given temperature and pressure, a non-equilibrium material, a glassy polymer, can have a range of density values. And so it doesn't obey the Gibbs phase rule. An example of this is shown in the literature here, the effective history on specific volume. And this is work from a guy in France, Kovacs, who studied this to death back in the 60s and 70s and early 80s. And he did on many types of material studies like the one that's shown here. He really liked polyvinyl acetate, which has a TG in the range of actually in the range of room temperature. And so what Kovacs was doing is measuring the specific volume of the polymer as he put it through various thermal protocols. And so the points that are shown here are the specific volumes in these units. On the other side is the thermal expansion coefficient, which is essentially the slope of these V versus T curves. And so he would start with a material up around 50 degrees C and start to cool it at various rates down to low temperature and measure the specific volume as the temperature went down further and further. And if he cooled it very slowly, so that this process took on the order of 100 hours, the material would follow this curve. If he cooled the sample very rapidly over just a few minutes or a few seconds here, it follows this curve. If you think about that for a moment, at least qualitatively, I hope it makes sense. That is, you start with the material in the rubbery state, equilibrium state at high temperature, and then if you cool it rapidly and the polymer chains can't reorganize to get to the specific volume that would be in equilibrium at one of these low temperatures before their molecular motion is effectively frozen out, then you wind up at a high value of specific volume. If you cool very slowly, so you give the molecules maximum chance to reorganize before they go through this glass transition where long-range molecular motion is effectively frozen out, then you wind up at a lower specific volume, that is at a higher density. And so if you cool the material slowly from a temperature above the glass transition temperature to below the TG, you can wind up in a more dense state than if you cool it very rapidly. And so these are examples where below the TG, this material at a given temperature and at ambient pressure has two values of the specific volume, depending on how rapidly or slowly it was cooled. And if you vary that cooling rate between these two values, you'd get a whole family of curves, and the density could be anywhere between these two limits. And you can imagine that if you're a small molecule sorbing into a polymer or dissolving into a polymer, if that polymer is more expanded or less expanded, this would have an impact on the free energy required to sorb that molecule into the polymer, and that would then have an impact on how much of those small molecules could sorb into the polymer. And so what Sardi and Doguieri did was they started from the basic expression for the Gibbs free energy in the Sanchez-Lacombe model, and instead of differentiating it and setting that derivative to zero to get an equation of state that would give the density as a function of temperature and pressure, that would be for an equilibrium material, they plugged the experimental density that was measured for the polymer, the out of equilibrium density, into this expression to calculate the free energy, and then took the derivative of that free energy with respect to the number of moles of penetrant to calculate the chemical potential of penetrant inside the polymer. And what this allowed them to do was to introduce an extra degree of freedom into the chemical potential expression for the penetrant and allow it to depend not only on temperature and pressure and the weight fraction of penetrant that's in the material, but also on the density of the polymer. And so the density of the polymer, rather than being fixed by thermodynamic equilibrium, could be set experimentally. And its impact on the chemical potential of the penetrant in the polymer was then obeying the same statistical rules as in the original Sanchez-Lacombe model. At equilibrium then, this penetrant chemical potential in the polymer would then be set equal to the chemical potential of penetrant outside the polymer. So if the polymer is sitting in an environment surrounded by a penetrant at a given chemical potential, then that chemical potential would be the same inside and outside the polymer, but the chemical potential of the penetrant in the polymer would now be given by a version of the Sanchez-Lacombe model that accounted for the actual density of the polymer, not what would be the equilibrium density. And so I won't go through again the details of the derivation here, but I will want to show you some of the results. And so this is a graph of data by Greg Fleming and Bill Koros of the concentration of carbon dioxide in a polycarbonate sample at 35 degrees C, and polycarbonate is a glassy polymer. And as the pressure of carbon dioxide in the environment surrounding the sample is increased, the concentration of CO2 goes up. And you may recognize this shape is one that we talked about recently as being associated with the dual mode model for gas sorption in a glassy polymer. Now, the dual mode model can describe these data, but only after you empirically fit the model to the data. It can't predict the data. And based on a fit of the dual mode model to this set of data, it can't tell you what would be the sorption isotherm at a different temperature, for example. So it's an empirical model. The line or curve drawn through the data now represents the so-called NELF model. You remember the Sanchez-Lacombe model, like the Flory-Huggins model, and the rest of them are statistical mechanics-based models, so-called lattice fluid models. The revised version of the Sanchez-Lacombe model to be applied to glassy polymers, Sarti and Doguieri called the NELF model, and that stands for non-equilibrium lattice fluid model. And so this is the NELF model description of those data. Now, what's important to note here is that unlike the empirical dual mode model, which has 3 parameters that have to be fit empirically to describe this data, there are no empirical adjustable parameters in this fit. So the NELF model could be applied in its equilibrium form, that is just the standard Sanchez-Lacombe model, could be applied to the gas phase of carbon dioxide to model the chemical potential of carbon dioxide in the gas phase. And the parameters to fit the carbon dioxide phase behavior are known in the literature. The Sanchez-Lacombe parameters for polycarbonate are known in the literature based on volume versus temperature and pressure data. And so those parameters are known. To get this isotherm, you take the known parameters for CO2 in the gas phase to calculate the chemical potential in the gas phase at a given temperature and pressure. You take the known parameters from the Sanchez-Lacombe model for polycarbonate and the density of polycarbonate. So the only piece of information that's needed to make this prediction is what is the density of the sample at the condition when there's no gas in it. And because it's a non-equilibrium material, that density value can change depending upon thermal history of the sample, as we've just seen in the work by Kovacs. And so Doguieri and Sarti took as the penetrant-free density is the only parameter in this model, and that you really have to measure experimentally. And armed with the density, then you can predict with no adjustable parameters these isotherms. Now, with an equation of state type approach, you could then predict isotherms at other temperatures or other pressures. If you have data, if you have a different gas, like methane, nitrogen, butane, for which the Sanchez-Lacombe parameters are known, you could predict the solubility of any penetrant using this approach. And they have, Giulio Sarti and his colleagues, since they first published this model, have gone systematically through the literature and have deployed it against a lot of different polymers and penetrants. It is As far as I know, the only fundamental model that's widely used to describe penetrant uptake in glassy polymers. It can capture another behavior of glassy polymers that's known as non-equilibrium behavior that's known as conditioning. So if you start with a sample of a glassy polymer with no penetrant in it, and again this is CO2 as an example, and you start to increase the pressure of CO2 on the outside of the sample, that material will start to absorb CO2. The CO2 will start to partition into the material, and it'll follow this dashed line. This point is at about 300 psi. And as this material has absorbed carbon dioxide, it's swelled a little bit. And if you stop here in terms of pressure and now start to step down in pressure and measure this gas solubility coming down, the values are not the same as they were going up. Why not? Okay, and so how did that come about? The swelling. The material is swollen a bit due to the CO2 absorption, and as you bring back the CO2 out, that swelling doesn't completely go away, and it leaves the material in a lower density state, and in that lower density state, it is energetically easier to put CO2 molecules in the sample. And so the solubility of CO2 is a function of the history, because the density of the sample is a function of its history. If you were to take a fresh sample now and come back up this isotherm to 600 psi, and then start to release the CO2 pressure, you come down along this curve. And again, it's different from the one at 300, and it's different from the one where the polymer has seen no exposure to CO2. At higher pressure, the sample will be more swollen. And as you start to remove the CO2, the sample can't relax completely, and it leaves more open sites, more Langmuir sites in the dual mode model parlance. And into those sites, you can have higher degrees of sorption. And likewise, if you go all the way up to 900 pounds and then come back down. And the NELF model can describe these data, the curves, and the dashed line are the NELF model predictions, knowing only the density of these samples at the penetrant-free condition. So once you've taken this sample back down here, take it out, measure the density, and with that information, you can predict the sorption, and likewise. So this gives the first ability to actually predict these sorts of hysteresis or conditioning effects in gas sorption or penetrant sorption in polymers. Now, I want to have a short discussion before we move off of solubility and start to talk about diffusion coefficients about the sorption of mixtures of penetrants in polymers. So in many practical applications, for example, in separations applications, a polymer membrane would always be exposed to a mixture of penetrants. It's never exposed, like we've done in the previous slides, it's never exposed to just CO2. If it's a natural gas separation, it's CO2 and methane. If it's a desalination, it's water and ions, and Lord only knows what else is in the water. But the separation membranes are typically exposed to mixtures of penetrants. And then those mixtures will, each of the component at equilibrium sorbs into the polymer according to its chemical potential. Now, if you have not just a penetrant-free, not just a polymer, but if you have a polymer that has, say, penetrant A in it, and then you expose it to a mixture of A and B so that B starts to sorb into polymer plus A mixture, you can imagine that the thermodynamics of having B sorb into that polymer plus A mixture could be different than having penetrant B just sorb into the polymer with no A present. And so that's what we'll talk about here briefly. So the big picture is that in rubbery polymers, so polymers that are whose glass transition temperature is below the use temperature or below the testing temperature, in rubbery polymers, penetrants sorb more or less independently of one another. And we'll see example of that in a moment. And so the total concentration is just the sum of the concentrations of all the species that sorb into the material. And in glassy polymers, the penetrants compete for these non-equilibrium excess volume sites, or the so-called Langmuir sites. And it's like, it's like 100 students competing for seats in this classroom, right? Not everybody's going to get in. Just the few and the condensable ones. And so we'll see an example of that. And I use the example of methane and butane, one because we've done a fair amount of work with that mixture, those mixtures in our lab previously. This is a prototypical separation for recovery of higher hydrocarbons from natural gas. Natural gas comes out of the ground. It's often saturated with water. It's methane, CO2, and a range of heavier hydrocarbons. And there have been some applications where membranes are used to remove those higher hydrocarbons to adjust the fuel value of the natural gas, and natural gas being essentially entirely methane. I also picked these two because they're fairly simple molecules in terms of their interactions. They're alkanes, and they're very different in size, very different in critical temperature and condensability. As you'll see in a moment, in some of these cases, butane is an 800-pound gorilla, and it pushes the methane around. It's a bully, essentially. A detail is that while methane and butane individually behave almost as ideal gases over, at reasonable temperatures and pressures, when they're in mixtures, they don't. And their compressibility factor or fugacity coefficient can be significantly different from one, which is the ideal gas case. And so we will express the results here not in terms of pressure, but in terms of fugacity, because this is the pressure of the components corrected for their non-ideal gas behavior, so that you get an accurate representation of the chemical potential of the gas in the gas phase, and that you calculate from equations of state. And so here is the sorption of butane uptake as a function of butane pressure or fugacity divided by its saturation pressure or saturation fugacity. And you can see that over a range of from -20 to 50 degrees C, all the data lie on a single curve. And in silicone rubber, PDMS, this curve can be calculated. It's the Flory-Huggins equation, essentially. So this is pure butane. Now, this is butane in mixtures with methane at various pressures and various temperatures, and the curves represent the pure gas data at these different temperatures, and the data points represent measurements of the solubility of butane in the polymer in the presence of methane. And what you can see from this is, well, there's a couple things. One is, as the temperature goes down, the solubility of butane goes up. That happens over here. I just haven't plotted it out, one isotherm at a time. But the solubility goes up. That's a general trend with gas solubility in polymers. And there's not much daylight between the curves and the data points, between the pure gas data and the gas mixture data. That is, butane sorption into silicone rubber is largely independent of any methane that's there. Now we're going to see in a moment, remember these sorption levels or solubility coefficients that are in the solubility coefficients being in the hundreds and sorption levels in the 40, 50 cc's per cc range. Methane is much less condensable than butane, and so its sorption, even at high pressure, these are 2% mixtures of butane in methane, right? So 98% of the gas on the outside of the polymers is methane. And then as the pressure of that mixture ramps up, you see more butane sorption, but it's almost in line with what you see in the pure gas case. That's not true for the methane. And so this is the methane concentration. You'll see it's significantly lower than the butane concentration as a function of methane pressure, and again, corrected for non-ideal gas effects of methane, call it fugacity. And you'll see that the solubility of methane in silicone rubber that has some butane in it is higher than the solubility of methane in silicone rubber by itself with no butane around. And as you go to lower temperature, this is at -10, -20, you see this effect as well. So the presence of the butane in this polymer is increasing the solubility of methane. Why is that? We'll have another look at it here. So this is methane solubility as a function of either butane pressure, that is fugacity, or as a function of the butane concentration in the polymer. And what you can see is that the solubility of methane is higher as the concentration of butane in the polymer increases. And there's almost a linear trend there with butane concentration. It's also helpful to know that methane is actually more soluble in butane than it is in silicone rubber. Okay, so these are data points. Some poor soul has measured the solubility of methane in liquid butane. Okay, imagine that as your graduate thesis project. It's basic thermodynamics. And so here's the solubility of methane in butane as a function of temperature, and here's the solubility of methane in pure silicone rubber. So what we saw in the mixed gas sorption case was that the presence of the butane increased the methane solubility. And then we come to data for the solubility of methane in silicone rubber and compare it to the solubility in butane, and we find that methane is more soluble in butane than it is in silicone rubber. So now imagine that you have a mixture of silicone rubber with some butane in it, and you start to contact it with methane. The methane finds that environment of the silicone rubber plus the butane to be more thermodynamically favorable than that of the silicone rubber alone. And so the methane solubility is higher as the butane content of the membrane goes up. And this is a phenomena that's well known in liquid mixtures, and we can actually apply a simple model from liquid phase thermodynamics to predict this behavior. And it is that the log of the solubility of methane depends on the volume fraction of PDMS times the log of the solubility of methane in PDMS plus the volume fraction of butane in the mixture times the log of the solubility of methane in butane. And so the solubility of methane in this mixture is just a weighted average of the solubility of methane in the polymer and the butane, depending on how much butane is in there. Okay. These silicone rubber, we've looked at dilation data in the past. Silicone rubber swells in the presence of these mixtures, and it swells in really controlled and intuitive ways. So the total volume change at, for example, 35 degrees C is a function of pressure for mixtures that are 98% methane and 2% butane, 96% methane, 4% butane, 6% butane, 8% butane. The more butane is in the mixture, as butane sorbs more into the polymer, and every molecule of butane is a good bit bigger than methane. So the more butane is in contact with that mixture, the higher is the swelling. And you can see these effects even more at low temperature, where the solubility of the butane is even higher. And some of these, the swelling here, you may imagine that you take a piece of plastic and just contact it with a gas and it doesn't swell much. Well, if you get the temperature low enough and the pressure high enough, this is showing like 20 volume percent swelling. And the extent of dilation is just really easily predicted from the concentration of the methane and butane in the polymer times their partial molar volumes that you get from just pure gas swelling experiments. So this is an example of additivity of volume, right? You have polymer, you mix some butane in it, you mix some methane in it, and the whole mixture swells just according to volume additivity. And here are the partial molar volumes of both methane and butane, and the dashed line is the for methane is their partial molar volume methane in organic liquids. And so the volume that a methane molecule takes up in the polymer is quite similar to the volume it would take up if it were just sorbing into a liquid like hexane or benzene. The size or partial molar volume of butane in the polymer is about equal to what its molar volume would be just in liquid butane. So again, this is very simple behavior in terms of the swelling. And now we'll look at the other end of the spectrum. We're going to look at the same data now, but in a glassy polymer. And this polymer is trimethylsilyl propyne, PTMSP. And when it was first discovered in the early 80s, it was for a long time the most permeable polymer known. Has this double bond, it really prohibits motion about the carbon-carbon bond, and then this really bulky side group up against the methyl group on the neighboring monomer unit really doesn't allow much molecular motion around subsequent monomer units. And as a result, this material has a disordered structure in the solid state that packs at very low density. And so what would you imagine density of a polymer would be in round numbers? And let's do it in grams per cc. That's the only units I can relate to easily.
1 gram per cc.
Gram per cc, 0.9 for polyethylene, 1.2 for these highly aromatic materials, 1.4 for a really dense, maybe crystalline material. This one is 0.75 grams per cc, lowest density of all known polymers. Okay, and what that means is that it has a very open structure, lots of free volume, and glass transition temperature is in excess of 250 degrees C. This material will thermally decompose before it will go through a glass transition. It really doesn't like to be in the rubbery state. And so then you can expect that it has, it will exaggerate the non-equilibrium sorption and ultimately transport and other properties. And so here are the sorption isotherms for methane on the left and butane on the right. And these are the pure gas, so one gas at a time as a function of pressure, and then as a function of temperature. As you go up in pressure, you see classic dual mode behavior, or this could also be described by the NELF model. As you go down in temperature, gas solubility goes up. In the case of butane, you see more pronounced dual mode effects and higher levels of absorption. And again, as you go down to low temperature, the solubility goes up. And to give you some idea of how we will analyze the mixture data, the dual mode model says that in a glassy polymer, the gas sorption is equal to the gas sorbed into the Henry's law or equilibrium region plus the gas sorbed into the non-equilibrium excess volume in the material, where Kd is the Henry's law constant, F is the pressure for an ideal gas. For non-ideal gases, F is fugacity, again to account for any non-ideal gas effects. CH prime is the Langmuir capacity constant, so materials that have a lot of non-equilibrium excess volume have high values of CH prime. B is a Langmuir affinity constant, so what is the affinity of a penetrant for those Langmuir sites? Both Kd and B tend to increase very systematically as the critical temperature of the gas increases. So the more condensable the gas is, the higher its critical temperature, the higher the values of Kd and B, the stronger is the affinity for the penetrant, for the polymer in general, and for those Langmuir sites specifically. So more condensable penetrants are generally more soluble in polymers than less condensable penetrants. And using model from competitive adsorption, for example, on microporous carbon, to extend this model, the concentration of two species, A and B, out of a mixture in the polymer is written this way. And we'll compare that to the pure gas version. So now each penetrant has its own Henry's law solubility. And instead of being total pressure or total fugacity, this will be the partial pressure or the fugacity of component A. You can think of this as the partial pressure of A in a mixture of A and B. And then each component has its own CH prime and B values. And in adsorption into zeolites or molecular sieves or microporous carbon, the way this competitive sorption is accounted for in a Langmuir model is by introducing an extra term here. So this is the concentration of A in the polymer. If it were simply pure gas, this would be all that there would be in that expression if you compare it to the one on the right. When there's a mixture of penetrants, this model is extended to have a second component here in the denominator, and this is a standard extension for calculating mixed gas adsorption onto microporous materials. And what it says is that at a given pressure of A, if you start to introduce another component in there, what happens to the concentration of A in the polymer? It goes down, right? Because if you start to increase the partial pressure or fugacity of B, this term starts to become, in the denominator, starts to become important. This overall Langmuir term is reduced, and then the overall sorption of A in the polymer is reduced. And that reflects the competition of A and B for the fixed number of non-equilibrium excess volume sites or fixed number of Langmuir sites. And likewise for B, equation 6.
How does the CHA prime and CHB prime compare to each other?
This will, so these capacity parameters, if you remember the units on them, they're cc's of gas at standard temperature and pressure per cc of polymer. And so the cc's of gas at STP is another way of writing moles. And so these Langmuir capacity parameters, in the simplest case, will simply scale with the size of the molecule. And that was the point in the previous lecture where we compared the CH prime value of carbon dioxide and polyethylene terephthalate as a function of temperature from the Paul and Koros work, and saw that CH prime went down almost directly in proportion to how the excess volume went down as temperature went up towards the glass transition temperature. And so underpinning that is that CH prime is proportional to the effective size of the penetrant in those Langmuir sites. Okay. So here again is the butane uptake. I'm sorry, the methane uptake as a function of pressure. And now we're at a fixed temperature, and this is pure methane. This is the methane sorption in the presence of just a tiny amount of butane. 0.05 atmospheres of butane in a mixture with methane in the gas phase. And this tiny amount of butane in the gas phase reduces the methane sorption. You go up to a little higher partial pressure of, or partial fugacity of butane in the gas phase, methane comes down some more. And at the highest, highest partial pressure, 1.62 atmospheres or fugacity, look, what does the methane isotherm look like? Henry's law. So what does that mean? Yeah. Can you imagine the nerve? It's throws and just, I mean, it's heartless, right? I mean, so here you see standard dual mode behavior, and then you put just a little bit of butane in that gas mixture. It sorbs into the polymer, effectively fills the Langmuir sites, and methane has got, only thing that's left is it can sorb into the Henry's law sites, but it can't get in to the Langmuir sites. Now, to show you an example of life not always being fair, what does the methane do to the butane solubility? Almost nothing, right? So you go, this is the butane solubility. Over here, there's no methane at zero on this axis. So here's the butane solubility as you go from 0.05 atmospheres of butane to 0.23 and on up in pressure. So this is just pure gas butane, you get butane concentration in the polymer. And then as you ramp the methane pressure in the presence of that same amount of butane in the gas mixture, there's almost no change in solubility. So the butane, the more condensable penetrant, can drive the methane out of the Langmuir sites. The methane, is just not condensable enough to change the solubility of butane. This is not a fair fight. And you can expect, and I picked this one because it's an extreme case. You can expect that if those penetrants were closer to one another in their molecular properties, so maybe rather than methane and butane, we would take ethane and propane, or butane and isobutane, things that are closer together in condensability. Then you could see that each penetrant influences both the others. But in this case, the methane is just not condensable enough to get in the way of the butane. And I haven't shown you yet, but this has profound effects on the transport properties. If you were to imagine that you are permeating methane through a membrane of this material, and I now start to co-permeate just a little bit of butane, what do you think happens to the methane flux through the material? Yeah, it's like, it drops, it can drop an order of magnitude, right? So a little bit of butane in the feed gas to this polymer can kill the methane flux, because most of the transport in this particular polymer is going through those huge amounts of the Langmuir sites. And so the summary here is that the light gas has essentially no measurable effect on butane, and the heavy gas, or the higher critical temperature gas, the butane, has a huge effect on methane solubility. And if you were to compare the values of the parameters over here, these affinity constants, which often scale with critical temperature, increasing critical temperature gives increasing B values, you can see that butane is, at least 100 times greater affinity parameter than methane. And so then you start to crank just a tiny amount of butane into this mixture, and it kills the sorption of methane. You can also do dilation on these materials. And so if this material has like a really high amount of non-equilibrium excess volume, and when penetrants sorb into that non-equilibrium excess volume, they can often do so without swelling the material. What would that do to the partial molar volume of these penetrants? Sorry?
It would be very
It'll
small.
be incredibly small. And so these are the dilation isotherms for pure gas methane and butane, and you start to get a sense of how of how small the partial molar volume is. That is, how little you swell this polymer when you start to put these gases in it. This dashed line is the volume that methane occupies in organic liquids at 25 degrees C. Here's the volumetric swelling of this polymer at 25 degrees C. So it's almost nothing relative to what you would see in putting methane into an organic liquid. So if you put methane molecules, say, into hexane or benzene or other liquids, you need about 53 cc's of volume per every mole of methane that you put in the polymer. Under the same conditions, you need like 20% of that volume to put the same amount of methane in PTMSP. So that means that you put an awful lot of methane in this material, and it doesn't swell very much. What would that do to the polymer penetrant density? Sorry? Absolutely. If I'm putting mass in, putting molecules into the polymer, but it ain't swelling, then mass over volume goes up. So you would see the density of these materials go up. That has real implications for the way that polymers interact with small molecules in general. It's a phenomenon known as antiplasticization. It's the word, you'll find it in literature. And what happens is that you'll see effects in things like mechanical properties. And so if you sorb a small amount of a penetrant into a polymer where it increases the density of the polymer, makes the polymer stiffer, right? So it's not just transport properties that change, can change all the dynamic properties of a material, including its mechanical properties. And here is the data for swelling in butane. And again, the dissolved volume, 100 cc's per mole, is essentially the volume butane would occupy in liquid state at 25 degrees C. And you can see that the swelling is less than that in the polymer. So here are the partial molar volume values that are calculated from those dilation isotherms. And okay, so this one's for methane. There's the partial molar volume methane would have as it's dissolving in liquids, here's the partial molar volume that it has in the polymer. So it almost doesn't swell this polymer at all. A value of 0 would mean that, that the methane doesn't swell the polymer at all. Butane is even more extreme. You don't see any swelling until you put, almost 20 cc's per cc of butane in the material, and then finally it begrudgingly starts to swell a little bit. But this material is unique, or is unusual in the sense it has a very, very high value of this non-equilibrium excess volume. And as a result of that, you see that not only in the solubility properties, I'll show you later, you see it in the transport properties, and you see it in things like these dilational or volumetric properties. It turns out that we can describe the dilation of mixtures of methane and butane using essentially the partial molar volumes from the pure gas data, and just assuming that the swelling is additive. So there's nothing other than additive volume mixing here, except that the effective volume that the penetrants occupy is really low relative to their true size, because they have all of this empty volume to sorb into. And that model, assuming just additive volume based on pure gas data, is shown here. It's not a perfect fit to the data, but it's a really good first approximation. And it assumes that the penetrants only sorb into the Henry's law domains. And the deviations you can see here will likely reflect the fact that that assumption is not quite 100% true. And with that, we'll end our discussion of solubility, and I'll move on to start a discussion of diffusion coefficients. This is lecture notes 10. And we talked about this just briefly right at the beginning of the course, but I'll remind you, the rate limiting step for small molecule migration in a polymer is the thermally stimulated motion of the polymer chain segments that open and close small gaps. We typically call them free volume elements in the polymer that allow the penetrants to execute random diffusion. And so small molecules like gas molecules that are sorbed or dissolved in a polymer will be vibrating about their lattice positions at ambient conditions about 10 to the 12th times per second. So there's, they have thermal energy, and that causes them to move. They're sitting confined by polymer chain segments, so they're sitting there, executing random molecular motion at very high frequencies. The polymer chains, because the monomer units are connected together, execute molecular motion on a much, much longer or slower time scale. But the polymer chains also are endowed with thermal energy, and so there is some motion in polymer chain segments. And from time to time, that random motion of polymer chain segments will open a gap big enough for the penetrant to go through. And if the penetrant goes through and that gap closes behind it, then the penetrant will have executed a diffusion step. And what was this mechanism called? Did anyone remember? This is the Red Sea mechanism in the literature. And we imagine from an activated state point of view here that the polymer chain surrounding a penetrant are viewed as these little noodles, and that as a result of thermal energy, those polymer chains from time to time will separate, and the penetrant is constantly vibrating within the space where it's sitting. And if it executes a step and the polymer chain segments come back in behind it, then it will take a diffusion step. So this is just emphasizing that it's the molecular motion of the polymer chains that gate penetrant transport. And I showed you this one earlier. It's molecular dynamics studies in poly-2,6-dimethylphenylene oxide. And here, the polymer has been built in a simulation box at its experimental density. It has been endowed with thermal motion, and then Newton's laws of motion are solved for each of the atoms in the backbone. Then oxygen and nitrogen molecules are unleashed inside this simulated polymer, and their motion through the polymer is tracked. And you can see that over time scales for oxygen of like 1,000 picoseconds, you can watch it move away from its origin via random diffusion. It spends an awful lot of time in at each diffusion step before moving on, sometimes coming back, but gradually it moves away from its origin. The same thing is true with nitrogen, but the jumps from one free volume element to another are rarer in the case of nitrogen. And in fact, here you see 3 steps for oxygen and only 1 step for nitrogen in these molecular simulations. And this is due to the fact that oxygen has what's called a kinetic diameter, or an effective diameter, of 3.46 angstroms. Nitrogen is 3.64 angstroms. So the way you remember these two is that the last 2 digits, 46 and 64, are flipped. So that difference of less than 0.2 of an angstrom, I mean, it's nothing, gives oxygen 3 times as many opportunities to execute diffusion steps in this material as nitrogen. Now, these displacements are on the order of angstroms, and the time scales are on the order of picoseconds. But you can go to macroscopic samples of PPO, polyphenylene oxide, and you can measure macroscopically the diffusion coefficients of oxygen and nitrogen through this material. Look at the ratio of them. It's 3.2. That microscopic phenomena that we saw playing out on the angstrom level on the previous slide over picoseconds is also observed in macroscopic measurements that are in samples that are tens or hundreds of microns thick and over time scales of minutes to hours to days. Now, typically, there's a couple different ways that we'll describe diffusion mechanistically, but a really common one is so-called Arrhenius expression, activated state theory, if you're familiar with that. And it says that the diffusion coefficient of a penetrant A depends on a front factor exponential of the activation energy of diffusion, EDA, divided by RT. So this is the way you describe, many rate processes where there's diffusion, in some cases viscous flow, chemical reaction, on and on and on. And we remember that from our discussions earlier that the diffusion coefficient can also be written as a product of a square of the jump length divided by the frequency, divided by the time scale for a jump, or alternately multiplied by the frequency of those jumps. Remember, this comes from the Einstein relation. Now, the frequency of jumps in an activated state process is given by the expression here on slide 6 from transition state theory. And it says that the frequency of jumps depends upon a group of constants out front that involves just a linear dependence on temperature, and an exponential term depending on delta G star, where this is the difference between the free energy of the system in the activated state and in the normal or non-activated state. So this is the basic picture from activation state or transition state theory about how rapidly those jumps can occur. When it takes a lot of energy to move to the activated state relative to the ground state or non-activated state, frequency of jumps is very rare. So you can imagine that in a polymer that is very rigid, so the molecular motion is very constrained, You require a lot of energy to open even a small gap in the polymer matrix. Jump frequency is lower. In a given polymer, the bigger the penetrant is, the larger is the gap size that has to be opened to let that penetrant through. The larger the gap size is, the bigger is the activated state free energy relative to the ground state free energy. Frequency of jumps is lower. So the frequency of diffusion steps goes down as penetrant size goes up, goes down as the molecular mobility, the polymer chains go up, or goes down. And this is again coming back to that little cartoon of diffusion through an activated state. Typically, the activated state free energy is related to the difference in enthalpy and entropy formally between the activated and non-activated state. This is again a result from transition state theory. And we can put these results together to get the result that's shown here on slide 9. Historically, this activated state enthalpy is written as the activation energy diffusion minus RT. That's just a historical way of relating this enthalpy to reach the activated state to the activation energy of diffusion. And we can then write the diffusion coefficient as shown here in the middle of slide 10 rather, and compare it to the expression I showed you on the first slide, right? This is the standard expression for, if you were just to write down what would be the expression, the Arrhenius expression for diffusion coefficient, you'd maybe write this. And that then tells us that this front factor is related to the jump length and to the entropy change associated with reaching the activated state. The cool thing here is that these parameters are related. And and this has been known for a long time, but even today it's not well appreciated. So it turns out Barer, a long time ago, observed that the activation energy of diffusion and this front factor term were correlated. We back up a second. So values of D0 and ED can't just be anything they want to be for a given system. These two parameters are very strongly correlated. There is a log linear relationship. These parameters A and B are empirical, but they're constant. A is independent of polymer type, has a value of 0.64. B depends on whether the polymer is rubbery or glassy, but then no dependence on the chemical structure of the polymer. I mean, look at this. This is out of a variety of penetrants and a variety of polymers. And these are the data for glassy polymers at the time, and these are the data for rubbery polymers. And that front factor in the diffusion coefficient is very strongly correlated with the activation energy. What does that mean in a practical sense? Well, I can take that relationship and put it into the Arrhenius expression I showed you on the first slide. And you get this expression. If I have a gas or a penetrant that is diffusing through a polymer, A and B are universal parameters depending on whether the polymer is glassy or rubbery. If I make one measurement of a diffusion coefficient, 1, I can calculate the activation energy. And I can then predict the diffusion at other temperatures. Think about that, right? Make a diffusion, as an experimentalist, this is very helpful, right? You make a measurement at one temperature and can predict transport properties at other temperatures. Now, I have overstayed my welcome with you today, and so I will stop here at this cliffhanger and not explain why this happens. But the next time, stay tuned, because we'll go through that. Thank you for your time today. And I have posted a homework assignment 3 on Canvas, and Rahul is eagerly waiting to collect homework assignment 2. Thank you.